it gives me a huge pleasure to be introducing my amazing colleague and dear friend Vince Poor from Princeton University. I told the speakers that I'm not going to try to read their bios because they're too long, and you can find them online. So I'll be giving non-standard introductions, and this, what can you say? He's a member of just like about every learned society that anybody can spell, and he's extremely well known. But I think one of the great things from knowing his work and knowing him is he's really one of the core people who have brought information theory and engineering and signal processing under one umbrella. He was just telling us how he's teaching a freshman course at Princeton on the history of technology in Princeton entrepreneurship. But this sort of truly holistic view, humanistic view, I would even say, of engineering, ranging from the math all the way to the application, is, as we all know, very rare. But that's really what makes our field advance, and this really is what makes big progress leaps possible. So, with that, Vince, thank you for participating, and the floor and screen are yours.
Okay, thank you, Muriel, for that really far too kind introduction. Maybe the best thing I could do now would be just to shut up and go straight to questions, but I have to give a talk, so let me get started with that. I'm going to share my screen. So again, thank you, Muriel, so much, and thanks both of you for organizing what looks like a really, really interesting workshop. Let me see if I can get myself off the screen here. So this is a workshop of networks of, for, and by machine learning. And of course, there are many kinds of networks, but one of the most prominent types of networks today are wireless networks. So what I'm going to talk about this morning, and of course it's going to be brief, is one aspect of learning and wireless networks. And so let me just motivate that a bit more in a second, but let me just point out that there are two aspects to the connection between machine learning and wireless networks. One is, using machine learning to optimize networks. And of course, communication networks involve many types of optimizations, decision-making, control, estimation, and so forth. And all of these are things that machine learning does very well. So there's a lot of obvious connections for using machine learning to optimize wireless networks or other communication networks for that matter. And the other side to that is using wireless networks, or particularly mobile networks, as platforms for machine learning. And that's what I'm going to talk about today. But before I do that, I'll use this opportunity to shamelessly plug a book that's coming out soon, I hope, on machine learning and wireless communications, which covers both of these aspects. And this is with Yonina Eldar, who's another speaker in this workshop, Andrea Goldsmith, and Denise Gunduz. Hopefully coming soon to a bookstore near you. So today I'm going to focus not only on specifically on using wireless networks as platforms for machine learning, but I'm also going to focus in on federated learning. And I'll talk more about that in a second. And this is how my talk is organized. I'm going to motivate edge learning in wireless networks. Then I'm going to talk about federated learning over wireless channels, and I'll talk specifically about scheduling. And I'm going to talk about privacy protection in federated learning, and I'll talk specifically about differential privacy. And then I'll bring up a few research issues. And this talk is going to be more impressionistic and not at all comprehensive. It's a very big field, of course, but in 20 minutes, I had to make some choices. And so I'm going to focus in on these particular things. So let me, first of all, by way of motivation, let me just give a very oversimplified view of the state of the art in machine learning today. Obviously, machine learning is not a new area. It goes back decades. It's had its ups and downs, but it's certainly in an up today, these days. And that's mainly been brought about by the fact that we just have tremendous amounts of data available today and incredible amounts of computing power in our handheld devices all the way up to the cloud. And I'll oversimplifying, I'll just mention a type of standard machine learning where it's implemented in the cloud in a centralized manner, and machine learning algorithms have full access to the data. And of course, this is enabled by state-of-the-art models, most prominently perhaps deep neural networks, which run in the cloud. And this is assisted by things like by software like TensorFlow and hardware like GPUs and so forth. So vastly oversimplifying the state of the art, but this is roughly one way to think about it. So, what does this have to do with wireless? Well, centralized machine learning, of course, is very powerful and has many applications, but it might not be suitable for many applications, such as autonomous driving, emergency response, healthcare applications like robotic surgery and other things, tactical military networks. And that's because these networks have certain things in common that make centralized machine learning not so suitable. For one thing is data is already typically born at the edge in these applications. It comes from iPhones, IoT devices, and so forth. There's limited capacity for uploading data to the cloud. Backhaul is limited. Latency is often a major issue in these kinds of applications. Data privacy is also an issue. I'm going to talk more about that later. And also in a lot of these applications like autonomous driving, you're really interested in what's happening locally. You don't care so much about global modeling and so forth. So these kind of applications and considerations motivate moving learning closer to the network edge. And we can think about sort of edge learning in two ways. First of all, on the left here, we have standard, so what I'm calling standard machine learning, where end user devices collect data, it's uploaded to the cloud, and the model building goes on in the cloud. Another model is federated learning, where end user devices collect data and actually work together to build a common model. Modeling is done at the end user devices. Local models are uploaded to an aggregator. It could be an access point or a base station. Aggregated models are then downloaded to the end user devices, and that process can go on iteratively until there's some kind of convergence. And then there's also fully decentralized machine learning, where there is no aggregator, and machine learning happens through peer-to-peer collaboration. Okay, I'm not going to talk about that today. I'm going to focus in on federated learning. So let me now focus particularly on federated learning, on scheduling and federated learning. But here I just want to illustrate the implications of using wireless channels on federated learning. And scheduling is one of the main issues that we have there. So here's a sort of basic architecture of federated learning. The basic idea, of course, is to enable end user devices to do machine learning without centralizing their data. So this is for maybe help to preserve privacy and also to minimize latency. And some key features, we have own device data sets. So end users keep raw data locally. Training is done on end user devices. They're trying to train a shared model. Multiple devices are training a shared model. And then there's federated computation. Now, these end user devices upload their trained models either by weights or through gradients to an aggregator, and the aggregator updates the shared model in some way and then downloads it back to the end user devices and who update their models, and this process is iterated to convergence. So enter the wireless channel. So when you do this over a wireless network, then of course communications to and from the access point needs to go through wireless channels. And of course the wireless medium is shared. There's finite wireless resources in any network. there's only a limited number of devices that can be selected in each update round. So if you think about an IoT network, there are many end user devices and only finite amount of bandwidth, say. So on any given update round, bandwidth has to be allocated to a limited number of devices. Also, because it's a wireless channel, transmissions aren't reliable due to interference and other impairments of the wireless channel. So a couple of natural questions that come up: how should we schedule devices to update trained weights? And also, how does interference affect the training? To look at this, we can look at this issue. We can look at some standard scheduling mechanisms. And I've just listed three here that I'm going to examine in a second. So one is random scheduling. So if we have K end user devices and N resource blocks, so N is less than K, obviously, or there's not a scheduling problem. We can do random scheduling where we, at each iteration, the aggregator selects N out of K end user devices at random. We can do round robin scheduling where we divide the end users into groups and then they're just selected sequentially. Or we can do proportional fair scheduling where signal to noise ratios are used to select which devices to upload at each iteration round. And we can look at how these perform and compare them. That's what I want to do next. So I'll just make the point that if an end user device is going to be part of a training update, their individual model can be successfully received by the aggregator only if, first of all, that device is selected by the scheduler. And secondly, that because it's a wireless channel, the received signal to interference plus noise ratio at the aggregator has to exceed a decoding threshold. That is, we have to have a good enough link in order for the model to be uploaded correctly to the aggregator. So we can think of a parameter theta, which is an SINR lower bound that has to be satisfied in order to have a successful model update, even when an end user is selected by the access point. And we can compare schedulers based on the metric of the number of communication rounds required to reach a sufficiently accurate solution. And here I'm going to zero in on a very simple problem where we're trying to optimize or say minimize a strongly convex function. So there are primal and dual problems. At optimality, primal and dual problems have the same solution. And an epsilon accurate solution here is just one where the solutions to the primal and dual problem are within epsilon of one another. So in this general setting, we can actually come up with lower bounds on the number of communication rounds needed for these three scheduling policies. So I think the actual expressions here are not very meaningful, but the parameters that come into play here are, first of all, theta, the SINR bound, epsilon, which is the degree of precision that we're trying to achieve in the total number of training exemplars distributed over all the learners. Alpha is the path loss exponent. It's a wireless channel. And then the learning at the end user devices is abstracted into a precision level beta, which just tells us something about how well learning can be implemented at the end user devices. Okay, so these are not very important in general, just the idea that we can get lower bounds on the convergence rates in these three cases given by specific expressions based on these parameters. So again, the expressions aren't very meaningful, but we can look at an example. One is the one on the left here is high SINR lower bound, high SINR threshold. The one on the right is for a low SINR threshold. And the message here basically is, at least in terms of these lower bounds, that if we have a high SINR threshold, which means that the link is not very good because we need high SINR to close the link or to decode the message, you see that proportional fair is the better of these three scheduling mechanisms. And on the right, when we have a small SINR bound, SINR threshold, which means that the link is actually quite strong, then round robin outperforms the other two. And this is intuitively reasonable because when we have a noisier or less powerful code or what have you, we need to pay more attention to SNR, which is the situation on the left. And when we have a stronger link, we can just, we want to just be sure that we poll all of the end users in sequence, and that's what's shown on the right with round robin. Now, these are just lower bounds, but we can actually confirm this with a real machine learning problem. And this is, in this particular case, we're looking at building a support vector machine on the MNIST data set, which is a handwritten character data set. And this just compares random scheduling to round robin. This is a low SINR threshold case. So we know in terms of lower bound that round robin is better. And it also is borne out here in a real example that round robin is better. On the left, we have loss, and on the right, we have accuracy. And you can see that round robin converges much more quickly. So this brings up the question whether, so we see that scheduling does matter in this problem. And we can ask the question, can we optimize scheduling? And of course, we don't ask a question if we can't answer it in this business. So the answer is we can try. And one metric we can use is age of information, which is a metric that has been introduced to analyze sensor networking, where in addition to the traditional metric of fidelity, we introduce a metric of data freshness to analyze and optimize communications. And here we can impose an age of information metric on each end user device. So if a device is selected at a given round, the age of its information drops to 0. Otherwise, the age increments by 1 on that round. And based on this metric, we can define an average age constrained in certain ways. We can get an optimization algorithm that can be solved on each iteration round to choose those devices that minimize the average age. And when we do that, we get an algorithm called wireless round robin. And here we, again, this is for fitting a support vector machine to the MNIST data set. And we can compare it to a baseline, which is maximum pack, which tries to choose at each update round, tries to choose the maximum number of devices to upload. And you can see here that wireless round robin is clearly better, both in terms of loss and accuracy. So we can, in fact, improve scheduling by trying to minimize the age of information metric. So I'm looking at the time, and I see I have about 5 minutes, so I'm going to just move on and talk briefly about privacy. And let me just motivate this a bit. I mean, I think probably most people here familiar with federated learning know that an early claim for federated learning was that it was privacy preserving because the data remains on the end user devices. But subsequently, studies have shown that this is not the case, and that in fact, end user data can be inferred from the updates, either parameter updates or gradient updates. And there's some pretty graphic examples, particularly for where the data is in terms of images, where you can almost reconstruct the complete image from the parameter updates. So it's clearly not privacy preserving in its native form. So privacy of end user data is a concern, particularly for some of the applications I mentioned earlier. So one approach to approaching this problem is to use differential privacy to protect end user data. And I want to talk about that briefly. So I think most listeners here probably know about differential privacy, but in case not, let me just say a word about it. So differential privacy is a type of privacy in which when you have two data sets, one that has private information and one without that information, but otherwise they're identical, they can't be distinguished by statistical query with high probability. And differential privacy, of course, has found its way into many applications. I think it's even used in the census this time. And one way to achieve differential privacy is to add noise to data. So it's a fairly simple mechanism for achieving it. And this is an approach that can be applied in federated learning where noise is added to model updates before they're uploaded. But this creates a trade-off between privacy and performance, because the more noise you add, the more privacy you get. But of course, that deteriorates the performance of machine learning. So it's interesting to consider this trade-off. And just one example is here. This is again with the MNIST data. We're fitting a convolutional neural network to the MNIST data. And what's shown here is training accuracy versus aggregation time for different levels of differential privacy. And in differential privacy, there's a parameter epsilon, which is an exponent that appears in the probability bound. And if epsilon, the smaller epsilon is, the more privacy you get. Excuse me. So you can see clearly as we go down from top to bottom here, as we introduce more privacy or add more a higher level of privacy to the data, we get worse testing accuracy. Okay, so there's a clear trade-off here. All right, so I got one more minute, so let me use it by talking about a couple of other research issues. First of all, in the example I gave for scheduling, I just abstracted the machine learning at the end user devices to this one parameter beta. But of course, end user devices, particularly in IoT, are limited. So there are a lot of fundamental trade-offs there in terms of in implementing federated learning in real networks. Also, the coding of coding is a big issue for uploading of models. This is basically a distributed source coding problem. There's correlation among the models and so forth. So there's a lot of efficiencies that can be gained there. This is not a big data problem. This is a sort of a small data problem. Learning at each of the end user devices is done with fairly sparse data sets. And so that means that we really should be looking more at a gray box type of machine learning paradigm where we incorporate domain knowledge and so forth. And also, I mentioned privacy. There are other approaches to privacy, over-the-air computation and so forth, that can be used. And also, in addition to privacy, there are security issues, because whenever you distribute the learning over end-user devices, there are, of course, always the opportunity for malevolent actors to enter the network and to either try to change the model that's being learned in some negative way, or introduce adversarial training examples or what have you. So there's a lot of issues here. It's a big research problem. There are many people working on this. I'll just flash up here a list of some papers from my group that have come out recently. And I think with that, Muriel, I'm just out of time, so I'll thank the audience and be happy to entertain questions or hear what others have to say about this topic.
Thank you. Thank you very much, Vince. That was a whirlwind tour. You've covered so many different topics. I actually already have a question here from Ariella in the chat. And she's asking about the quality of the wireless channel for each device or the device capabilities in your modeling.
So I'm sorry, let me look at the question specifically here. So
I can.
Oh, I see. Well, that's an excellent question. So in this particular model, we've just assumed a homogeneity across all devices, but there's a lot of work, and I think it's very important work on multiple issues of heterogeneity, heterogeneity of data sets, heterogeneity of wireless resources, heterogeneity of device capabilities. I grossly oversimplified those issues in this thing, but there is certainly a lot of work along those lines. It's a good question.
Yeah, and a follow-up question is, I think you assume that the data is IID, right? So it's another open research. Federated averaging works very well for IID, but then there is also research challenges for non-IID data.
Exactly, yeah. So that's another type of heterogeneity, and in this in this particular experiments that I showed, the data was assumed to be IID, but there is also a lot of work on that. These are devices are sampling the environment, and the environment, of course, is not necessarily independent from device to device, and that's another big issue, and it does affect performance, of course.
Yeah, thank you.
Thanks for your question.
Yes, thank you, Ariella. I have a question here from Manoj. The question is, do global weight updates ensure the improved performance in the local node?
Oh, that's a good question. So, each node, of course, on each round tries to do its best to fit the data it has, but when it gets the downloaded model is not necessarily the best model for its data, right? So the idea is to converge to a common model rather than to converge to a model that's optimal for each end user device. So it's not necessarily the case that each end user device is going to wind up with an optimal model based on its own data. Yeah, that's a good point.
Yeah. I had a little bit of a question with regards to the privacy, if I may, Vince, which is actually the privacy that you're looking at is you have different nodes developing, in effect, their own models, and then you're pulling the models together, right? But what about having pre-processing of the data and then having a single model working off of the pre-processed data, but not necessarily combining separate models?
Well, that's a good question. I mean, I'm not quite sure I have an answer for that, Muriel, but I let me just, maybe I'll take this opportunity to say something I didn't say in the talk, in that there are multiple kinds of privacy to be considered, and maybe this does go to your question. I mean, there's the issue of sort of malevolent actors trying to learn private things about the end user devices, locations, or other things. There's also the so-called curious aggregator issue, which, in other words, there are questions of who are you trying to keep things private from. And I think maybe I don't really, not sure I quite understood your question, but I think maybe that's part of the question is who is it that we're trying to keep things private from?
It's very related to that, yeah.
And I think the answer depends on that. I mean, if you're worried about whatever goes out over the air being intercepted by eavesdroppers who are going to, use your private data in some evil way, you do one thing. If you're worried just about the curious aggregator, you can do another thing. So in terms of privatizing the data before you do machine learning, since that happens within the device, I don't know. I'm not sure exactly how that would work. But if you had a malevolent actor had access to your device, perhaps you might want to do some kind of differential privacy on the data as you're collecting it before it goes into the device's memory.
Yeah.
I could see that. Yeah, I haven't. It's the first time I've thought about that, so I don't have a good sense of how that might work. But I think it's an interesting idea.
Fantastic. Thank you. So we have a question here from Raj Velichetti. Would scheduling updates in particular ways, say using round robin or age of information, introduce bias into the machine learning model?
That's a good question. I mean, I think in this sort of pristine example I used where everything is IID and all the devices have the same, the end user devices have the same capabilities. I don't think so. But in the question that Ariella brought up, or the issue Ariella brought up, is that this is not really the case because the data is often non-IID. The devices have different capabilities. Some of them can converge more quickly than others. Some of them have more data than others. And with all those different kinds of issues, the scheduling doesn't become so simple anymore, right? And by the way, there are scheduling algorithms. This was a very simple one. There are scheduling algorithms that take account the quality of the models on the individual devices. Mohammed Amiri, who's a postdoc here at Princeton, has worked some on that problem. but I think the short answer is yes. In a real situation, I think the scheduler, the type of scheduling can affect the model itself. It's a good point, and I think in practice it is something that has to be considered.
Thank you. The next question is from Benoit P. Claudel, and is, have you considered looking at other topologies than a base station talking to all end users? For instance, having communications among the end user devices.
Yeah, so that's a great question, and there is federated learning without a separate aggregator. So there are other models for federated learning than the one I discussed here today, and one of them is the one you're suggesting, Benoit. Also, there's just like I mentioned at the beginning, this fully decentralized type of learning where you don't have any kind of model aggregation, and you only have localized peer-to-peer connections. And there are a lot of results on convergence to common models and so forth for that kind of topology as well. So, again, this was, as I said, not comprehensive, really more impressionistic when I was talking about today, but there certainly are other topologies that are of interest in practice and for which there's been a lot of work done.
Thank you. And one last question, I think, here from Bin Lee, depending on we may just have time for one other, but how does the age of information affect performance of machine learning, for instance, in accuracy? And the question is do you have any intuition on this, Vince?
Well, I mean, we saw in that example that minimizing the average age improves accuracy, right? So that's how, I mean, that's the end result. Now, what's the intuition behind that? I mean, it may go back a little bit to Raj's question, or maybe it was, I think it was maybe.
Yeah, I think it was Raj's. Yes,
it was Raj's question. Once we start having devices that aren't all the same and data that's not IID and so forth, age is still pristine, right? To think only about age is the only metric. We start needing to add other metrics in there, like some measure of quality to each device's model, for example. So I think age definitely seems to, minimizing average age definitely seems to improve things in terms of rapidity of convergence to a common model. But that common model, I think, is going to be affected by all the other things that came up in Ariella's, in my response to Ariella's question about heterogeneity in the network. So in real life, a lot of things can happen that have to be considered. And I think in these examples I gave here, again, it's mostly impressionistic, just to show to highlight some of the issues that come up. But there's certainly many others, and they're going to affect performance. Yeah.
Thank you. I think maybe we'll be able to just sneak in a little bit of one last question, maybe while Ariella gets set up. This is by Zishan Kalim. I think it's a little bit related to a previous question, but it's somewhat different, so I'd like to bring it up. What is the update period for updating the weights in federated learning? Do you have any specific criteria there?
Oh, that's a good question. So, I mean, this again here, we just assumed that we're updating after all the end users have converged to their local models. Again, it's been abstracted to that, but there's a lot of work on when to update, and particularly when you have heterogeneous capabilities. So some learners will converge more quickly. Do you update then, or do you wait for everyone to converge and so forth? So I think this, I don't have a pat answer to the question, but I think it's certainly an important one. And again, when you get into the reality of heterogeneous devices and so forth with heterogeneous data sets, certainly the issue of when to update is a big one. So that's it. I think now it looks like Ariella is up. So let me just thank you. The organizers, thank everyone for your questions, and thank you for listening. And I look forward to the rest of the workshop. Thank you all.
Thank you, Vince. We're clapping on Zoom. We're Zoom clapping.
Thank you all.